Hi, I'm Grayson Evans, KJ7 Uncle Mike. Welcome to my introductory video on hollow-state homebrewing, the art and science of building stuff with thermatrons, what some are still calling vacuum tubes. I was licensed as a ham in 1963 and spent much of my life in electronic product development, mostly boring solid state. But I got interested in building and restoring vacuum tube amateur radio equipment in the early 1990s, and I've been doing it and writing about it ever since. The purpose of this video is to teach you the basics of thermatron operation, as well as how to adapt typical homebrew design and construction techniques to thermatron circuitry. I'll be referring to some of the material in my fantastic book, Hollow State Design, throughout this video. The book has everything you need to know about thermatron technology, including how to build thermatron projects. It's available from Lulu, eBay, and the electric radio magazine bookstore, and I'll have links to it in the show notes, assuming I can figure out how to do that. Some of you might be unfamiliar with the term thermatron, what many in the US still refer to as vacuum tubes. Let me clarify this for you. This is a tube. This gizmo is a valve, and this puppy are thermatrons. Any questions? I didn't think so. I think the best way to teach something is to do it. So we're going to start with a very simple project that you can build in a couple of hours that actually does something useful. Sort of. I'm going to start with a thermatron version of the famous Michigan Mite transmitter. This is a very simple crystal-controlled oscillator that can be used as a QRP transmitter. A lot of you have heard of the Michigan Mite, popularized by the Soldersmoke Blog. There are countless YouTube videos and posts across the internet about it. A single transistor, a variable cap, a coil, a crystal, some resistors, and a capacitor. The idea of the original circuit was to utilize a very low-cost color burst crystal used in analog color television sets at 3.579 megahertz in a very simple Pierce crystal oscillator circuit. The crystal provides the feedback path that causes the circuit to oscillate at the frequency of the crystal. The tuned circuit can be inductively coupled to an antenna to make a transmitter. This puts the output signal in the CW portion of the 80-meter band, on the common Michigan Mite calling frequency. Of course, you can use other crystal frequencies as long as you change the tuned circuit accordingly. There's a lot more information about the circuit and the Color Burst Liberation Army on the Soldersmoke Blog. It's a great resource. To make a thermatron version, we need to substitute a thermatron for the transistor and make the necessary component changes. Now, the purpose of building a simple project like this is to show you how to build with thermatrons with a minimum of complexity and things that can go wrong. But it will utilize everything you need to know to build thermatron projects. But like any new project, it's best to start with a little noodling, as Pete Giuliano says, before you start soldering parts together. And the first step is to draw a new schematic. But what thermatron to use? The choices are basically a triode or a pentode. You can read up on the different characteristics of triodes and pentodes in Chapter 5 of Hollow State Design. To keep the circuit simple, I'll use a triode. Not as much gain, but fewer components. The triode cathode, grid, and plate is roughly equivalent to the NPN transistor in the original circuit. I redrew the original circuit using a 6C4 triode, a very common and easy to use tube, but almost any medium gain triode would work, even using one of the triodes in a dual triode such as the 12AT7. The thermatron version doesn't require a tap on the coil for feedback. The components in the thermatron version serve a similar function. L1 and CV form the resonant tank circuit at 3.759 megahertz. Frequency selective feedback to the grid is provided by the crystal. The capacitor blocks DC from the crystal, and the resistor provides grid leak bias to the tube. and the tube circuit is link coupled to the antenna, just like in the original circuit. The crystal acts as a series tuned circuit and provides the necessary 180-degree phase shift to sustain oscillation. This is a very basic circuit, and assuming I can get it to work, I may add some enhancements such as an output low-pass filter. With a working schematic, I like to prototype the circuit to make sure it works and to finalize the component values. So the next step is to collect the parts. But since this is my first Thermatron related video, I thought it would be best to devote a little time on where to get them. Now, Thermatrons are not in short supply. There were billions of these things made, but you may not be familiar with the common sources. Of course, the best sources are Hamfest, but if you missed out on the last one, there are many online sources such as Antique Electronic Supply, Vacuum Tubes Inc., and so on. Any tube made after 1939 is still available, with prices typically in the $2 to $7 range. Are transistors a heck of a lot cheaper? Of course. But which of these is cooler? Making things with Thermatrons is not to make them cheap, but to make them cool. And trust me, building stuff with Thermatrons builds character. Oops. Well, you drop one of those transistors on the floor, shop floor, it's pretty gone. These guys? Yeah, I'll be back. Thermatrons are one of the best examples of industrial art. These shots from Thomas Mayer's Love of Thermatron blog show some of the amazing internal structures. Most of these Thermatrons were assembled by hand. Many still are. The original Michigan Mite project used a 3.759 MHz color burst crystal, mainly because these are cheap and still very available. Again, you don't have to use this frequency, but it's part of the spirit of the Mite. The only other component I need to make or scrounge is a coil, and then find a matching capacitor that will resonate the coil around the crystal frequency. While almost any tuned circuit resonant at the crystal frequency will work, better efficiency can be obtained if we do a little more noodling on the tuned circuit values. The tuning capacitor and inductor in the tank circuit should be selected for the optimum reactance at the frequency of operation, and should be equal to the Thermatron plate resistance at the operating conditions, divided by the Q of the resonant circuit, which will probably be in the 10 to 12 range when operating. Of course, more information about this and additional coverage of transmitter circuits is covered nicely in Chapter 13 of Hollow State Design. The datasheet of the 6C4 shows an average plate resistance of about 7,000 ohms for Class A operation, and the characteristic curves verify it. Now, you don't have to be that precise, but it provides a good ballpark value. This gives an inductor and capacitor reactance of about 580 ohms. At 3.57 megahertz, my iPhone electronics app gives a value of 26 microhenry for the coil and 76 picofarad for the capacitor. I was hoping to use this nice open air coil I picked up at a Hamfest. It's a real beauty, ain't it? But it's only 18 microhenries. Can you believe that? Anyway, maybe next project, huh? Alright, so I decided to just DIY the coil on a piece of 1-inch PVC. I just wound a bunch of 24 gauge enamel wire till I had about 26 microhenries. It doesn't have to be exact. Mine is 50 turns close spaced on the 1-inch PVC. You could also use a toroid for a more compact version if you wish. This one is 65 turns on a T80 red core and gives about the same inductance. The variable capacitor needs to cover about 75 picofarads mid-range. Now, prototype circuits tend to have a lot of stray capacitance, so a little less than 75 is fine. I found this compression cap in my collection. It tunes from about 30 to 120 puff, so I'm going to give that a try. You can test that the coil and capacitor resonate where you want it with something like a grid dip meter, or by exciting the circuit from a signal generator and watching the amplitude on the scope. I set up the signal generator at 3.75 megahertz loop coupled to the coil, and I've got my scope connected across the LC network here. So I'm going to tune it and make sure I can get a resonant peak within the tuning range of the capacitor easily. So it looks like the mid tuning range of the capacitor, so this LC combination should work fine. The circuit also needs a way to couple the energy to the antenna. The simplest and oldest way is just loop couple the signal by adding a few turns of wire around the coil. This isn't the most efficient way to couple to the antenna, but it's the simplest for now. Back in the 1950s and 60s, the ARRL handbooks had quite a lot to say about link coupling, including a formula to calculate the number of link turns. It's really just the formula for matching impedances using a transformer. In our case, it works out to be about 4 or 5 turns over the primary winding. This should be in the middle of the coil. Something like this works fine. Like many homebrew builders, I like to construct my projects on a piece of copper-clad circuit board. This makes it easy for prototyping since everything can be glued or soldered directly to it. But until a few years ago, I was pretty frustrated by a lack of a way to easily solder or glue the thermatrons to the board. Fortunately, Rex Harper, W1REX of QRPme fame, came to the rescue with a set of Thermatron circuit pads he calls Me-tubes. It consists of 10 solder pads especially designed for mounting different types of Thermatron sockets. The panel has V-scores for breaking off single tube pads. The pads can either be superglued to a piece of PCB stock or mounted using screws and standoffs. You just solder regular tube sockets to the pads. I'm using a 7-pin socket and pad for the 6C4. I found the best sockets to use are the PC style, since they provide a large pin area to solder to the pad. Ceramic versions of these sockets are available from online stores for about $1 to $2. The nice thing about the pads is they provide plenty of room to tack solder lots of parts to a single pin, making it really easy to add or remove parts. Prototyping with these things is fast. I just glue it down. The tools and equipment you're going to need for Thermatron projects are basically the same as for solid state construction. The only difference is you're going to need the power supply to furnish the two B+ in the 50 to 200 volt range and the 6.3 volt AC or DC filament voltage. You can easily build one, but I would recommend a surplus supply. There were lots of high voltage power supplies built during the Thermatron era, and you should have no trouble finding one at Hamfest or eBay without much searching. One of the most common and well-designed bench high voltage regulated supplies was the Heath IP17. If you can find one of these, it's all you need. It provides 2 variable regulated high voltage supplies, 400 volts and 150 volts. Plus a 6.3 volt and 12.6 volt filament supply. This is a typical example of a high voltage supply you can build in an evening. The meter is optional and you can add your own bells and whistles. You will need a high voltage transformer that has a filament voltage winding. These are still made nowadays by Hammond and others and sold from many online stores. Chapter 8 in Holostate Design, Thermatron Homebrew Techniques, has a lot of detail on test equipment and power supplies, including DIY versions. Dealing with high voltage just requires some common sense caution. When you turn on a high voltage supply, just make sure you're not touching any part of that equipment. If you need to make a measurement, make sure the negative lead from the test equipment is connected to ground before you turn on high voltage. Use only one hand to place the other lead to make your measurement, keeping your other hand in your pocket or behind your back. When you turn high voltage off, make sure you give enough time for the filter capacitors to discharge and short high voltage to ground before you touch anything. If you need to work on the power supply, make sure it's unplugged from AC power first. With all the parts in hand, I can finally start building this thing. But we're not quite done noodling yet. It's a really good idea to do a physical layout of the circuit before you start gluing. Erasing is easy. Let me show you. At this low frequency, the layout is not critical, but I want to orient the tube pad so it makes connection to the rest of the circuit easier. There is no connections to pin 1 and 2. The filament is on 3 and 4. 5 is the plate. 6 is the grid with connection to the crystal. And 7 is the cathode. I included a phono connector for a key and a BNC for the antenna. I like to provide little wire loops to connect scope probes and wires from the power supply. I glue the socket pad down first. Then mark the locations I'll need solder pads and glue down each pad. Tricky for me. Sorry, I'm old and I shake a lot. Then I super glue down the coil and I glue the variable cap. Then I melt some solder where I'll mount the connectors and make ground connections. Next, I solder down the key connector and the output BNC. Then melt a little solder on each pad. This makes it easy to tack solder on the parts. Now I'm ready for the parts. First wire is the cathode to key connector. Then the 100K grid resistor, the crystal, and the capacitor. Then I'll wire the plate to one side of the tunable cap and coil. Then the high voltage bypass cap. And the high voltage connection to the tuned circuit. Then I wire up the filament leads. This includes wires to attach the cables from the power supply. Then the output link wires to ground and the BNC. Oh, I don't want to forget the Thermatron. There you have it, folks. Mighty Mite in 2 minutes flat. After a final check of the wiring and solder joints, including the resolder of a pin, it's time to fire it up. I'll get the scope probe ready on the plate to monitor the waveform and connect a key, then the filament, and B+ cables. Then I'll turn on the power supply and initially adjust it to 150 volts. Okay, with the scope probe connected to the plate side of the tuned circuit, what we have here is the joy of oscillation. What we've been shooting for this whole video. Sure enough, it works. Now this is quite unusual because my projects never worked the first time. But it was a pretty simple circuit. All right, so if I tune the capacitor again, There we go. Now, I've got a 10x probe, 5 volts per centimeter, 20. That's about 200 volts of AC on the plate side of the tuned circuit. Not bad. Pretty good output. And if I try it with my key, there we go. Pretty good. The 6C4 will continue to oscillate even at really low voltages. Let me show you. I can tune it down below 25 volts. Perfect for a single-digit milliwatt operation, if you're into that sort of thing. I'll hook up the second channel so you can see the plate on channel 1 and the grid on channel 2. Go. Boink. There's the plate voltage we've seen before, and there's the grid voltage. Notice 180 degree out of phase, just as advertised. Next, let's see what kind of output power we can get into my Homebrew 50 ohm dummy load. Attached to the output. Drops it off a little bit as you'd expect. Let's take a look at the output signal. All right, let me go down into the millivolt range and retune that puppy. Oh. Okay, let's take a measurement here. Looks to be about 845, 850 millivolts on the scale. That works out to about 8.5 volts peak to peak. And we're at 150 volts. Let's see what it is out of curiosity at 200 volts. 200 volts gives me about, we'll call it 12 volts peak to peak. Not bad. We need to calculate what that is in watts. The conversion from peak to watts into a 50 ohm load is pretty straightforward. And that works out to about 180 milliwatts and 340 milliwatts respectively. Definitely QRP. The output of the spectrum analyzer shows a nice clean CW signal. The second harmonic at 7.2 megahertz is down about 33 dB from the fundamental. Not bad with no filtering. It's highly dependent on the Q of the tuned circuit. The waveform looks great on the scope, and the note sounds good on the station Collins receiver on the other side of the room. I hope you can hear it okay. Next thing I want to try is to hook it up to an outside antenna to see if I can at least get it to show up on the reverse beacon network. I won't bore you while I do that, but I'll let you know the results. This is a fun little transmitter and a great project to start experimenting with thermatrons. And there's a lot more experimenting you can do. Try tuning the plate circuit to the second harmonic. You could work dual band operation, 40 and 80. Add a cathode resistor somewhere between 100 and 1,000 ohms. See what that does to the output. You can also try a pi network output coupling instead of this link coupling baloney. And if you get adventurous, try using a pentode circuit instead of the triode. If you can get any of these to work, I'd love to know about it. Send me an email. Oh, I don't want to forget my shameless commerce plug for Hollow State Design 3rd edition. There's a lot more Thermatron circuits design and homebrewing info in here. It's available from Lulu, eBay, and the Electric Radio Magazine bookstore. If you're not getting Electric Radio Magazine, you're missing out on a ton of Thermatron related articles, even some I wrote. Now, you can always email me with questions or suggestions, particularly if they're good ones. I may have another Thermatron related video up someday soon. This little transmitter deserves a simple Thermatron direct conversion receiver. Don't you think? 73 from KJ7 Uncle Mite.